Today's Pierre Elias, who is a cardiology fellow at Columbia University Irving Medical Center and someone who recently completed a 2-year postdoc right here in Adler Perotte's lab. Warm welcome to Pierre. Pierre, take it away.
Hi, everyone. Thank you so much. I'm excited to chat with you all today and tell you a little bit about what we've been working on. Many of you have been involved with different parts of this, so I think it should be pretty exciting. Let's just make sure that you guys can see the same thing I can. Okay. Can you see full screen for the presentation? Great. So again, thank you so much for having me. Really excited to chat with you all about kind of what I've been up to in Adler's lab and working with many of you and people kind of across Columbia and at other institutions. These are my disclosures. We have been lucky enough to have multiple industry sponsors who have worked with us through much of this. So I just want to start with why deep learning and machine learning matter in the field that I'm in, cardiology. So I spent a decent amount of time doing research in medical informatics, whether it's electronic health record research and understanding utilization or building risk scores, and now more recently in things that we would call AI or deep learning based. And I think there are specific places where deep learning, and for the purposes of this talk, we basically mean convolutional neural networks and other forms of neural networks with many layers, many trainable parameters, over 50,000 to 1 million. There are specific places where I think they actually can make a difference. So the first thing I'll say is that when you're using tabular data, and by that I define it as kind of traditional electronic health record variables, I think machine learning is rarely significantly better than traditional statistics. So when you have well-featured data, whether that's age, laboratory values, demographics, other things where we have very well described how the variable has an impact on an outcome, right? Where like if we have an abnormal lab value, we ultimately decided that an abnormal lab value starts at a certain level and continues and increases. And we've kind of prospectively validated that in order for it to be a lab value we continue to measure. When those features are already known, I think ML is rarely significantly better. And instead, there's a challenge to automate the analyses, right? So there are many risk scores out there that could actually greatly improve the way that we clinically practice, but probably the problem there has to do with workflow. So I think there are many situations where ML would be amazing to use and could be better than traditional stats, but maybe it's 5 or 10% better. And really the problem is something about the workflow, something about the access to the data prevents people from using even standard risk scores or standard approaches like logistic regression in order to improve the care that they're providing. And those are problems where it's tough, I think, for machine learning or deep learning to make a dent. Imaging, though, I think is different. The features within images and the pixels that represent an image are poorly known. Electrocardiograms are going to be an imaging modality we talk a lot about today, but there's a huge swath of what we call an electrocardiogram that doesn't really even have a name. We have a few features on the electrocardiogram that we've given names, but there's lots of pieces in between. And there's a huge amount of data being left on the table. An electrocardiogram is something that we've done 10 million times at New York Presbyterian. And every single one of those electrocardiograms has over 60,000 data points. And it's something where I, as a cardiologist, may take 30 to 45 seconds to interpret. So there's a huge amount of data that's still there, even with something as simple as an electrocardiogram, let alone more advanced modalities. And traditional statistics are really poorly equipped to analyze this sort of data. We've also seen some pretty significant and interesting achievements in the last couple of years from machine learning and deep learning approaches applied to cardiology. Atrial fibrillation is one of the most common abnormal heart rhythms, and it puts you at increased risk of stroke. And basically what we saw was a machine learning algorithm that was able to look at an ECG that was completely normal, but say this is a patient who has some degree of atrial fibrillation, even though it wasn't physically present on that electrocardiogram. We've also seen them be able to match clinicians' ability to look at ultrasounds of the heart and determine how well the heart is squeezing. And we've seen it outperform kind of all the traditional risk scores that we've had for the last 20 to 30 years in predicting cardiovascular mortality. I think of this as one of the most interesting studies that I've seen in the last few years. So this came out of a group in China and was published in JAMA Cardiology in 2019. So when our heart beats, there's a slight variation in the amount of red blood versus blue blood that you can see in our face. And these imperceptible differences can be picked up through special types of cameras. And what this team did is they basically looked at training a deep learning model on people's faces and being able to pick up when there was that difference in red blood versus blue blood. And from that, they were able to infer people's heartbeats. And from the regularity of their heartbeats, they could decide, was the patient in normal rhythm, what we call normal sinus rhythm, or were they in this very common abnormal rhythm that puts you at increased risk of stroke and where we need to give some people blood thinners called atrial fibrillation. So they just trained this model on people's faces and they were able to detect atrial fibrillation from videos of people in the waiting room of a cardiology office with a high degree of sensitivity and specificity. So to me, this kind of speaks to the creativity and possibilities that deep learning can allow for our ability to kind of contact with either contactless approaches or cheap diagnostic approaches, detect disease and take better care of patients than we are right now. So my nickel is that deep learning models are going to fundamentally change how we order, acquire, and review medical imaging over the next 10 years. And what we're trying to do here at Columbia, as well as with New York Presbyterian Hospital, is build a world-leading center where we can develop, validate, and deploy these deep learning models for early disease detection, particularly in cardiology, but hopefully and eventually in other fields as well. So this was something that I was extremely passionate about. It was why I came to the Department of Biomedical Informatics and worked with Adler and many other people. And the first steps was just getting the data organized. I've done this multiple times before for other projects at other institutions, and I knew how painful that was going to be, but it was the necessary first step. So we created something called CRADLE, the Cardiovascular and Radiologic Deep Learning Environment. So the first problem is that we had all of these legacy systems that have different forms of cardiac data. It was messy, disorganized, not centralized, and not easily accessible. And all those things need to be fixed. So CRADLE was our solution for that. So we have over 1 million echocardiograms, 9 million electrocardiograms, tens of thousands of stress tests, chest x-rays, PYP scans, and cardiac catheterizations, basically making one of the largest cardiovascular imaging data sets available in North America. This is one of the values of working at a place like Columbia or across New York Presbyterian. When we can do things at scale, we have this incredible ability to collate a very large amount of data. So the first thing was the tabular data, so like the imaging reports, the measurements that we make, all of that needed to come into information systems and servers that were much more accessible. So many of you know about Jupyter, which is the place that we make track requests and get access to a large amount of clinical data. And it's basically a copy of production data for research purposes and analytics purposes as well. So none of this cardiac data was there. So the first thing we did is we made sure that we were actually creating images for all of our research servers so that people could easily access this data, not just myself, but other people around the institution being able to have access to it. And that we better understood what were kind of all the quirks available inside of our data that we had to deal with before we could say it was appropriately pre-processed. The other thing we had to do was create imaging data pipelines. So basically, how are we going to be able to say we have a group of patients, like patients who have gotten heart transplants, and say, I want the chest x-rays on all the patients who have heart transplants, and I need the actual images for this specific form of deep learning. So we actually created imaging data pipelines that work across the institution. So whether your imaging was done 10 years ago or today, pre-Epic or post-Epic, at Columbia, at Cornell, or at one of our NYP-affiliated hospitals, there was one place everyone could go so that they could directly pull out that data. And lastly, we wanted to make sure that we had deep learning environments that were accessible to a large group of different people. So as you can imagine, doing projects like this, I work with people here in the Department of Biomedical Informatics. Then I may work with analysts on the New York Presbyterian side who would never have access to research servers at DBMI. And then we've also had multiple engineers from industry, people from Twitter and Google who have come to basically do sabbaticals and work with us. And they're not going to be able to look at any form of PHI or have access to data on the Columbia or the NYP side. So we were able to kind of create implementations, each with their own limitations, where people could be working on the data either from a research server on the Columbia side, from Azure instances on the NYP side, or from Google Cloud Compute instances, which were completely de-identified with IRB approval for people who were not affiliated with the institution, but still wanted to do some of this work. So after we had built out the infrastructure, we actually could do some of the fun and interesting things that we were interested in. So a lot of machine learning research today looks like this. We have a human expert's interpretation, which is the gold standard. And the goal is for your new model to get closer to that expert than the current state of the art. We see this not only across medicine, but really any field, right? You know, a human expert can tell the difference between a dog and a cat with 99.8% accuracy. You know, current models can do it with 95% accuracy. Your model does it with 97% accuracy. Our approach for our research is a little different. And the approach is, can we actually exceed physician performance? So there are all sorts of important problems out there where I, as a physician, would be a really terrible benchmark to set. I should not be the gold standard. Instead, there are things that if you give me that specific imaging modality, I can't answer, but we can get a very definitive answer that the patient does or does not have a disease if we look at an upstream, more expensive, but more accurate diagnostic test. And so what we do is we make our gold standard this upstream, accurate, but more expensive diagnostic test. And the goal is for our model to outperform human experts given the same data that a human expert would be given. So here's one example of that. This is our project called Valvenet. So aortic stenosis is when one of the valves in your heart gets tightened, and when it becomes severe, it can actually be quite life-threatening. You can also have the valves in your heart become leaky, which we call regurgitation or insufficiency. These valvular lesions are diagnosed with an ultrasound of the heart, which is called an echocardiogram. Electrocardiograms, which are this picture up here in the top right corner, these little waveforms that you've probably seen on TV many, many times, these are not diagnostic for aortic stenosis or any valvular disease. And if you asked me as a cardiologist, can I detect aortic stenosis from an electrocardiogram, I would not be much better than a chimpanzee doing the same thing. I'd probably, you know, bat 55% instead of 50%. Yet, we do 9 electrocardiograms for every 1 echocardiogram at NYP, and they're much, much cheaper. An electrocardiogram costs about $50, an echocardiogram costs $2,000 to $4,000. So what we did is we take the electrocardiograms done on patients who've also had echocardiograms, and then we generate labels to say this person does or does not have valvular disease. And then we train a model just on the electrocardiograms to see if we can detect what a human expert like myself could or could not. So our goal was to develop a deep learning model which analyzes ECG waveforms to detect patients with left-sided moderate or severe valvular heart disease as determined by echocardiography. And we looked at kind of the 3 most important left-sided valvular heart diseases: aortic stenosis, aortic regurgitation, again, where it's leaky, and mitral regurgitation, where the mitral valve being a different valve in your heart. And we looked to see, could we detect each one of them, and could we detect if any of the above 3 were present? So we took 620,000 electrocardiograms that were performed within 1 year of echocardiography on over 100,000 patients across 3 sites at Columbia: New York Presbyterian Allen, which is our community hospital, Uptown, Columbia University Irving Medical Center, which is our main site, and then all the adult patients at Morgan Stanley Children's Hospital. We excluded the electrocardiograms where we had incomplete labeling data, or we felt like there was something critically abnormal about the electrocardiogram that would limit analysis. We then broke this up into train, validation, and test groups. What was interesting is for the train group, we allowed it to learn from every ECG associated with a patient who was in the train data set. No patient was allowed to be in train, validation, and test. They could only be in one of the three. But because we didn't want the model to either be biased or our results to be biased about those patients who may have many, many more electrocardiograms when we were looking at the validation and test groups, we only allowed one ECG per patient in the multi-site validation and multi-site test groups. Then we had a fourth site, which was a complete holdout test site, where the model never saw any patients from that site, and it knew nothing about the prevalence of disease at that site, the patient characteristics at that site, nor did we account for any changes in the way that the data was captured at that site. This is the Valvenet model. We won't spend too much time on this, but those of you who work with convolutional neural networks will see that the underpinning here was the residual block, which is very common in ResNet. So the fundamental challenge here was many of these convolutional neural networks are originally created for two-dimensional images, pictures. What we were putting in was raw waveform data with 12 channels, each sampled at 250 hertz. So ultimately what we ended up with was 12 by 2500. Now, over the course of a year of experimentation, we tried a large number of architectures. We tried recurrent neural nets, LSTMs, a wide variety of things from both the literature on audio data, since these are waveforms, as well as imaging data. And what we found was consistently, we got as good, if not better, performance when we followed convolutional neural networks rather than recurrent neural nets or LSTMs or similar approaches. Moreover, we looked at a huge degree of complexity, models with 500,000 trainable parameters to models with 50 million trainable parameters. And we found very little difference in the total performance, despite having training times 10 times as long. So we ultimately decided on an architecture here, which was a 1D convolution specifically generated to deal with a ECG waveform, which was 12 by 2500 here. And largely leaning on using residual blocks as the cornerstone for the development of the model. We also ran the model with just the raw waveform or including tabular data that is regularly available when you get an electrocardiogram. Things like patient's age, sex, and then these specific characteristics of an electrocardiogram and conduction that are often seen. And then the model would give us a prediction between 0 and 1 of how likely it thought they were to have moderate to severe valvular disease. We won't go into too much detail here, but we did look at what was the average age of our populations, as well as the prevalence of the disease. The one thing that I will point out that was very interesting to us is our holdout test site, NYP Lawrence, was a very different patient population compared to the combination of the three sites. You can see here the average age is around 62 to 63 for our combined test sites, whereas at NYP Allen, it is an older population with an average age of 71%. And we didn't include it because the data was pretty poor quality as far as race and ethnicity goes, but it is also a significantly different racial and ethnic breakdown at NYP Lawrence in comparison to our other sites, which we thought was an interesting and good test of the model. Will it work well at a site where the patient population is inherently different? So these are the results of our model's performance. So we had receiver operating characteristic curves with AUROCs ranging from 0.79, with aortic regurgitation being the worst, all the way up to 0.87 for aortic stenosis. And the combination model had an area under the receiver operating characteristic curve of 0.83 in our holdout test set. We also looked at how did the model perform across a variety of subpopulations. So we saw pretty similar performance between males and females, but we saw that as we increased the age of the population, there was a significantly decreased odds ratio, which is very common. Amongst younger patients, they're very unlikely to have this disease. And if they have something atypical about their electrocardiogram, it's going to be likely much more obvious compared to older populations where they can have a lot of different disease processes that show up on their electrocardiogram that may look similar to the model finding valvular heart disease. So This was not surprising, but it's still very interesting to see a total difference in odds ratio of nearly 10 to 5. So halving when we looked in the kind of the oldest population in our group. When we think about deep learning in cardiology, and we'll talk a little more about this, one of the things that I think really matters with this kind of first version of introducing deep learning and machine learning into clinical practice is clinicians are going to think about the precision of the model or the positive predictive value. And the reason for it is right now we're screening patients who have undetected disease. And the way that we can imagine this working is we would run this model on a large group of patients who are candidates, they're at an appropriate risk, or they have some reason to be included in running the model. And we'd be able to go to a cardiologist and say, listen, we looked at your patient panel, and 3 of your patients came back positive when we ran this Valvenet model, which means we think these patients may have moderate to severe valvular disease. If we could tell them that the positive predictive value or the precision of the model was 33%, we could say, we think all 3 of these patients have the disease, but the positive predictive value is 33%. So likely 1 in 3 of these patients does have the disease. That cardiologist or that clinician can then say, will I send all 3 patients for whatever the next diagnostic test is in order for 1 of them to come back positive? And while there's a lot of different ways to think about results and how to interpret results from these sorts of studies, when we're trying to get people to adopt really an entirely new approach to clinical medicine, we think the positive predictive value is going to be the thing that they most key in on, because they're going to try and understand, is it worth me sending my patient for a potentially invasive, dangerous diagnostic test in order to figure out if they have this disease or not from a model that works in ways that I may not fully understand. So as you may know, the positive predictive value or the precision is largely dependent on your underlying prevalence level. Well, here's the rub. In these populations, it can be very hard to know what is the prevalence of disease. We have estimates from studies, but it's hard to know how well does your current population replicate with one paper done on some similar population 5 or 10 years ago in a different part of the country. So what we did is we looked at the area under the precision recall curves, and we modeled what would the positive predictive value at various recall thresholds look like depending on the prevalence. And this is the sort of information that clinicians are not comfortable with. You can even see here, we say precision, and then in parentheses, we put positive predictive value, because these are words that just aren't used in clinical research and in the papers I would normally be reading. But what we did want to do is say, well, how good are these models and are they worth deploying? So one arm of our research has been looking at when is it cost effective to employ one of these models? And these are some of the fundamental challenges we deal with when we think about deep learning version 1.0. And we can see here that if the prevalence of the combination label is between 5 and 10%, and we're willing to only find maybe half the total patients, we can have positive predictive values of around 25%, which in our field for finding a disease like this can actually be quite good. I also use this as a baseline for when people come and ask me, oh, should AI be used in this clinical project? I tell them, does an odds ratio of 5 make a significant difference? Do you have a point in clinical care where if you had an odds ratio of 5, yes versus no, would that help you decide what to do for the patient next? Because across many studies in my domain, this is kind of what I'm consistently seeing as a real world result is we can potentially have a 5-fold increased likelihood of the patient showing up with a disease. And we can also see aortic regurgitation, which is the least prevalent of all of them. It's dismal, right? It would be really, really hard to isolate a model to just aortic regurgitation and find it. And that would be a losing proposition kind of across the board. But aortic stenosis, mitral regurgitation, the diseases that are a little more prevalent, those ones you have a better chance of finding. The last part that I want to talk about here is just saliency mapping, which is our approach of trying to understand which features of the model using to make these predictions. So there are a wide variety of different saliency mapping techniques. We use many across our different projects, but here we're using specifically one called SHAP. The red pulls the model towards a positive result, and the blue pulls the model towards the negative result. The few things that I'll kind of point here. One, what is interesting is the way that a residual network architecture works, and particularly ours, is pretty instantaneously across the convolutional neural network. We're looking across all the leads. So rather than just having one of the channels, like channel 2, channel 3, or AVR, giving us all the information, we're getting at least some of the information across all the channels, because it's very quickly looking across all 12 channels together in order to try and make a determination of what is and isn't important. The second, and we'll talk about this a little more, is as a clinician, it's very hard for me to look at this and get anything more than a Rorschach test. We do see the models focus on specific parts of the electrocardiogram over and over again, but it's very hard to be convinced that I can look at this and learn something from it so that I myself could go back and try and detect aortic stenosis or any of these other diseases on my own. So what are we doing now? We have successfully built a retrospective model that can detect moderate to severe valvular heart disease using over 100,000 patients' data, and have shown that it works well across 4 different test sites. So we've actually started a prospective clinical trial here at Columbia, where we've taken all of the patients who are above the age of 65 who don't have a history of valvular disease and have an electrocardiogram in our system, but don't have an echocardiogram in our system. And that was around 37,000 patients. And we ran the model on all 37,000 patients and got risk scores for them. And we're actively enrolling 200 patients in a prospective clinical trial where we see where the model thinks is their risk. We call them and we bring them in for an echocardiogram to see do they or do they not have moderate to severe valvular heart disease. And this is really one of the first instances where people are doing prospective clinical trials in this way of deep learning. And the hope is that we can build these early detection models using deep learning kind of at a system-wide approach. That patient who came in for a routine knee operation, had someone do an electrocardiogram and no one ever listened to their heart, or they never saw a cardiologist, may be the exact sort of person who has undetected valvular heart disease that we could do something about. And from a personal standpoint, I've had patients come in very, very sick and we're not able to do anything for them. And it's one of the worst feelings when you have a patient who's otherwise healthy suddenly become very ill, and you know that they're too far gone for you to make a meaningful difference. But if they had gotten the right intervention 6 months, a year, 2 years prior, it could have made all the difference in how long they were going to live. So the hope is that we actually can be building models that work like this. And the next thing we have to do is test it like we would any other therapeutic. So we do something similar for another disease space. This one's called cardiac amyloidosis. So cardiac amyloidosis is this protein folding disorder that leads to deposition in the organs, and particularly the heart, and it can cause heart failure over time. The real sad thing about cardiac amyloidosis is it's one of these diseases that's really a slow burn that happens from when you're young all the way into your 6th, 7th, 8th decade of life. And so it's very hard to notice the symptoms because they're coming on very slowly. And the usual story is someone slowly has a worsening heart, and then sometime in their 60s, they become pretty short of breath, and they're found to have heart failure. And then they do the normal standard workup for heart failure, and they give them the normal treatment, and they don't get better. And people say, well, that's weird. I don't really understand why. And then another year or two goes by, and they start getting worse and worse. And then finally, someone says, maybe we should refer them to an advanced heart failure specialist or a tertiary care center. And then someone there says, well, have we thought about cardiac amyloidosis? So on average, patients will see 4 clinicians and wait 24 to 36 months before getting a formal diagnosis that they have cardiac amyloidosis. For the longest time, we had no treatment for this disease other than giving someone a heart transplant. And oftentimes by the point that they present, they would either be too sick or too old to get a heart transplant. That recently changed about 2 to 3 years ago when a new medication came on the market that can essentially stop the disease in its track. The rub is that it only works in stopping further progression of the disease. So you have to find the disease somewhat early on if you're going to be able to treat the patient. So we have a therapeutic, but we have to find these patients early on in the course of the disease if we're going to take care of them. And to date, no screening test is available for cardiac amyloidosis. And that really kind of remains the holy grail. So this comes from a study that myself and colleagues published a couple years ago, where we looked at the patients here at Columbia who we had scanned for the disease. So people come in, and here at Columbia, we developed a scan that allows us to non-invasively check to see if someone has this disease. And what we've seen is that when we look at the green lines here, we've doubled the number of scans that we do per year, and yet the rate of positivity has not changed. And what we believe is that there are many more patients that remain undiagnosed with this disease. So what we did is something very similar as we did in Valvenet. We took a large number of electrocardiograms from patients who have gone cardiac amyloidosis evaluation, built an ECG model based off of it, and then predicted the probability that they have cardiac amyloidosis. And we were able to achieve an AURC of 0.85, a precision of 54%, and a recall of 74%. What we're doing now is we're including additional information that we think is critical, such as abstracted clinical data from the electronic health record and data from echocardiograms, so that we can figure out how well does the model do with just a waveform versus including this other data that we believe is very, very important. An interesting thing about this disease is one of the earliest presentations of it is carpal tunnel syndrome. Particularly if patients have bilateral carpal tunnel syndrome, it's a red flag for cardiac amyloidosis. But there have been studies that show when you look for patients who develop cardiac amyloidosis, many of them got carpal tunnel releases done 5-7 years before they were formally diagnosed. And if you look under a microscope, you'll find amyloid deposits, since the amyloid goes everywhere in their body. So we're also running the cardiac amyloidosis discovery trial, where we're running the model on a group of heart failure patients who we believe are at high risk for this disease. And we're bringing in 100 patients at the highest probability of undiagnosed disease and having them undergo pyrophosphate scanning. So here, the risk is a little higher. We're irradiating these patients. With Valvenet, we're just doing an echocardiogram, which is an ultrasound of the heart. But here, we're really putting our nickel down and saying, we're genuinely worried about this disease. We know this disease is deadly, and we want to find it early, and we believe it's worthwhile to expose these patients to radiation in order to figure out if they do have cardiac amyloidosis. One thing that's surprising is how much do you need a deep learning model to discover things that are unseen versus just run things at scale in order to find patients who should otherwise get treatment. So we have over 2,000 patients above the age of 60 who've had an echocardiogram in the last 3 years, who have LV wall thicknesses greater than 1.5 centimeters and no PYP scan. So one of the hallmarks of this disease is an infiltrative cardiomyopathy. So it makes the walls of the heart very, very thick, very thick. A normal heart wall is about 0.9 centimeters. So this is easily 2.5 standard deviations away from the norm. And this is what some of the echoes of these patients look like. And these are very, very atypically thick walls with a speckling pattern. None of these patients have been formally evaluated for cardiac amyloidosis. All of them would warrant it. So sometimes just doing things at scale allows us to find patients who are at high risk for disease. And other times the deep learning model really does need to see things that, that we don't see. So right now we're running multi-center retrospective validations with Cornell, Stanford, UCSF, Cedars-Sinai, and Geisinger Health System. One of the things we've learned is move the models, not the data. Getting data use agreements in place is nearly impossible, but being willing and comfortable sharing models with one another and finding content experts at each of the places doing similar work allows us to really improve the quality of our model and test things more easily. We've chosen clinical problems where we have personal expertise. We can vouch for it and say this is a real problem, and where we have collaborators who are authorities in their fields who can kind of help ease the adoption of deep learning version 1.0, because we want to build things that people are actually going to use. And lastly, we want to treat it like any other therapeutic drug or device. So to do that, we have to run prospective clinical trials, because we think that's where the field is at right now. It's one thing to do large retrospective cohorts, but in order to change the way people clinically get practice, we have to meet them where they are. And where they are is randomized prospective clinical trials. And that's the exciting thing right now. I want to tell you about one more project that we're doing, which is called LVHNet. So this is some phenomenal work that I've been working on with Shreyas Bave and Victor Rodriguez, as well as many others, where we are trying to do something kind of audacious. So chest x-rays are the single most common diagnostic image of the heart in the world, but almost never generate meaningful information about heart abnormalities. They tell us lots about the lungs, but really the only word a radiologist is going to use about the chest x-rays are about the heart in the chest x-ray is cardiomegaly, which is pretty useless. It doesn't really generate any specific next step or treatment. So what we wanted to do is ask ourselves, could we create better labels than cardiomegaly looking at a chest x-ray? And thus, could we garner more meaningful information that could lead to actual clinical decisions from the chest x-ray? So we sought to train an algorithm on chest x-ray images captured within a certain amount of time from echocardiograms to detect abnormalities that radiologists currently are not. And if so, we could repurpose the most common imaging test in the world, at least of the thorax, as a screening tool for the most common cause of death in the world, namely heart failure. So we aim to detect stage B heart failure, which is when you start to have structural abnormality of the heart. Normally, right now, we don't think to do an ultrasound of the heart, an echocardiogram, until someone is symptomatic. And we think that there's a high suspicion that it's their heart. But if we had a cheap, non-invasive way to say this is someone who's at high likelihood of structural abnormality of the heart, we could then determine, oh, this is someone who should go for an echocardiogram and someone who needs additional treatment to try and prevent heart failure from getting worse. So we looked at left ventricular hypertrophy, both the normal variant and the more severe variant, as well as the dilated left ventricle. These are kind of the three things we look at for stage B heart failure. And we were able to generate a model with excellent AUROC here at Columbia. We're currently validating it at Stanford, as well as precision recall curves that we believe would be meaningful. So a positive predictive value of 45 to 48% at a sensitivity of 90% for predicting any one of these three things. And here the goal is to say who should or shouldn't get an echocardiogram. So if we could look at a chest x-ray and say there's something wrong here and someone warrants an echocardiogram, that would be immensely helpful. We also looked at the diagnostic read of cardiomegaly and how good is that at detecting actual cardiac structural abnormalities compared to our model. So this data is being revised and we're now having 5 radiologists overread this. But what we found is that our model is more precise, more sensitive, and has higher overall accuracy compared to our radiologist calling cardiomegaly. We want collaborators. We want to work with other people who are doing this sort of work. And so we've also built tutorials to get people going. We have free GitHub libraries that teach people how to extract all of the electrocardiographic waveform data from soup to nuts, how to generate their own data if they don't have access to any for toy problems, a wide variety of different deep learning approaches with TensorFlow, Keras, and PyTorch all available. And we make this freely available and we walk people through it. And we're actually doing a 3-hour workshop at AMIA this year, all about getting people into deep learning and cardiology. And we certainly invite you all to come join us Saturday at 8 o'clock in the morning for the workshop. And we try to do similar workshops on the cardiology side at American College of Cardiology and other major conferences. This really comes from how painful it was in my first year just to get access to the data and figure out some of these basics. And they're the sort of things that once you solve it once, they don't really need to be solved again, but we need people actively sharing and building repos and sharing libraries. And so that was one of the key things that we wanted to accomplish. So I could end right here and have this nice, pretty, rosy view that deep learning is going to have this amazing impact in cardiology and other medical fields, and that everyone should do it, and you should invest in any company that uses these buzzwords and call it a day. But like any research, you get to show the good results, and people don't really see how the sausage is made. But I do think it's important to talk about what are some of the cornerstone problems that I personally see in machine learning and deep learning, at least as applied to cardiac imaging, that I think are important for the field to address, and I think can be excellent research ideas for people. I put this photo in because I wanted to make the point of what do I think is missing before I'm ready to have a robot doctor colleague. This is like one of the first Google images when you type in robot doctor. But really, I put it in because these poor women look genuinely terrified of their new colleague, and so there may be more than one problem with having a robot doctor. But today we're just going to focus on what are the research and technical problems, not the social ones. So in the large scheme, really, I think what's missing right now from deep learning approaches, at least what is being published in my field and what we're seeing, is the model lacks context, lacks the ability to integrate varying amounts of information, and lacks the ability to show its work. And we'll walk through each one of those things. So the first is we do not effectively learn from patient priors. So whether you're a cardiologist looking at electrocardiograms or echocardiograms, or you're a radiologist looking at a CT scan, one of the first things you're going to do is figure out, does the patient have the same imaging modality from a prior point in time? Because we fully accept, while there is a bound of what is normal for the population, what's most important is what is normal for the patient. So when we last saw the patient, what was their physiologic state? Were they having a heart attack at that time, or were they perfectly fine? And what did their electrocardiogram look like at that time versus now? So the patient prior is an incredibly powerful thing. But almost all of the models that are convolutional neural network based or recurrent neural network based do not have an effective way to include patient priors. One, they're not set up to deal with the varying number of patient priors one patient may have versus another. Two, there's been a limited amount of research and fully understanding how do you take the fact that they've occurred at various frequencies and with various density into account. And three, the models themselves essentially are just meant to look at a single image. Otherwise, there can be competing information that the model can greatly struggle with. What if the patient has had 3 EKGs done this week? I run the model 3 times, and 2 of the times it gives me one answer, and 1 of the times it gives me a different answer. You can face real significant problems in understanding how to interpret the model in this regard. Also, we're particularly interested in how much does that matter? I think for certain problems, it matters a lot, and for other problems, it doesn't matter at all. But knowing how much models improve when you use this data is critical. And there's a lot of open questions on how model architecture needs to evolve to handle this. Is it more complex convolutional neural networks? Is it multiple models run in series? Is it entirely different architectures that are better able to handle variability in density, frequency, and total size of data? All of these, I think, remain serious open questions. Second, we don't learn from enough disparate data sources. So if I have a Dr. Robot colleague, they may be able to see things on an electrocardiogram that I can't see, but I need them to be able to look at that electrocardiogram in context with all of the other information that we have. Because very, very rarely do we just use a single piece of imaging or a single piece of information to ultimately make a decision. Rather, we are looking at it in the context of everything. So how do we look at electronic health record data, an electrocardiogram, and a CT scan in one model? This is a surprisingly tricky problem. It's somewhat easy to combine one imaging modality with tabular data, but understanding how one model can adequately learn from all disparate data types is quite challenging. The learning rates that are most ideal for different modalities within one single architecture may be very, very different. And it really brings up some classic ensemble learning challenges. And we won't go into that today, but these are problems that are somewhat solved in other fields in machine learning, but have not really been solved to my view within medical imaging in particular. As we talked about briefly, how do we handle varying amounts of available data per patient? This problem keeps coming up over and over again. If I want to include more than just a single image or a single scan, understanding that different patients are going to have different amounts of data is critical to getting the most out of what we already know about that patient. A perfect example of this comes from a Nature Scientific Reports paper from 2020 from some of our colleagues at Stanford. They looked at 7 different approaches for multimodal machine learning, not multitask, but how do we combine information that we have when it's, you can see CT scans, laboratory values, medications, vitals, ICD codes, all of these different pieces. And they saw relatively significant differences in the performance across these. But when I spoke with our Stanford colleagues and they applied the same sort of approach of checking 7 different ones for a different project, the results were entirely different. So we live in a world where so often we have these thoughts about how should we modify an architecture in order to deal with a problem. And the answer is, why don't you just try all of them and see what works best? And that often may be a reasonable approach to get the best answer for today with the information that you have. But we lack a larger, more disciplined methodology for understanding how do we decide to combine disparate pieces of information into a single architecture and know that what we're seeing is the most effective learning rate across all of these different imaging and data modalities, and that that's going to hold true at different sites or if you combine different types of data. We have a real multitask problem as well. We build hyper-specific models. So I take my model and I train it, and it's meant to just find valvular disease, when in reality, the prevalence of that disease may be pretty low. And what I should do is say, well, can I build a model that finds X, Y, Z, and everything else in between that would be concerning enough where someone should go get an ultrasound of their heart? What's interesting is there are real challenges here. So LVHNet, the project that I've worked on with Shreyas and Victor, we had a really interesting finding. So when we first started, we looked at 4 different labels instead of 3 labels. We had included a 4th label of thick hearts, which is called Hypertrophic Cardiomyopathy. And when we included that label, the model not only did terribly on that label, it brought down the performance of all 3 other labels significantly. And so we realized that the best thing we could do was abandon that label entirely. But we did see the model suffer significantly when we tried to extend it just to another cause of a thick heart wall, let alone looking for a very different sort of pathology. So we have real challenges in building generalizable models that work. I think we have somewhat generalizable architectures that can work well across different problems, but a single model that can look at a wide range of diseases, I think, continues to elude us. And lastly, can we learn from the models? What I would love, and is one little holy grail for myself, is if we could have a model that detects something that doctors can't currently detect, where we had a saliency mapping technique that could look at that, and we could teach the doctor it, and then the doctor could go and prospectively learn that technique and apply it and prove that it does work and that they could learn it. Because that really is what should happen. We have a long history in medicine of building new technologies, CT scanners, MRI scanners, and as we're going along the way, creating new findings where we say, oh, patients with this disease tend to have this pattern. So we have a long history of saying, we'll learn from technology and we'll discover new patterns as we go along that we may have not seen to begin with, and that we should learn those patterns and teach them to new physicians. So there's no reason why that can't happen here if we can have deep learning models that effectively do that. But I think there's 2 big problems. One, the techniques we use for 2-dimensional imaging, like GradCam, applied to 1-dimensional data don't work very well. And even for 2-dimensional data itself, I think there's a great deal that is lacking. So Here's just one example. So this is what happens when you have a heartbeat from an electrical standpoint. This is what an electrocardiogram does. The first top two chambers of your heart depolarize, and that's called the P wave. And then there's a little bit of time. And then the ventricles, the two bottom chambers of your heart, they depolarize, and that's called the QRS. And then there's a little bit of time, and then they repolarize, and that's called the T wave. So this is what one heartbeat looks like electrically on an ECG. And what we'll do is we create these kind of criteria, right? So left ventricular hypertrophy is when one of the walls of the heart is very thick. And this is what we'll teach people. We'll say, oh, look to see if you see this kind of abnormal dip right here after the QRS complex, or look to see if the total height of the QRS complex is greater than a certain amount in these leads or these channels. And then you combine these things and you say, okay, these are my criteria. These ones are called the Sokolow-Lyon index for saying someone has a disease, but we're looking at the amplitude, the width, and the characteristic or shape of the ECG. And we can create these patterns like here, S1Q3T3. This is kind of a classic pattern that someone has a blood clot in their lungs. And again, we're looking for these abnormal waves that don't normally exist in these channels. And when we see this combination, we say, aha, this is a bad sign and it means something. And we can even give odds ratios to these things like T wave inversion or ST elevation or their heart rate being here. This is how, as clinicians, we think about stuff and how we communicate information and teach information to one another so that we know when we're looking at a patient, we're talking about the same thing. This is the best that we have from an electrocardiogram saliency mapping standpoint. So much of that is lost. All I know is that from this time to this time, the model was greatly activated and pushed towards a positive result, and specifically in this channel compared to other channels. But I don't know if it has anything to do with the amplitude. I don't know if it has anything to do with the quality of it. I don't know if it has anything to do with the shape of it. So a huge amount of information is really being lost in these one-dimensional techniques these one-dimensional data where, we're applying 2D approaches to multi-channel one-dimensional data, but we don't really have better approaches right now. This is LVHnet. So this is some phenomenal work by Victor where, he's applied GradCam here to 100 chest x-rays. And what we want to know is the model, these are all true positives, is the model being activated by the heart? So you can see the actual image here and then what it's being activated by next to it. And you can see 100 times out of 100, that model is being activated by the heart. It's very consistently focusing on this part of the thoracic cavity to decide, yes, this is a big heart. It's not looking at any other abnormal structures, and rarely does it actually look at pacemakers or other medical devices that that could potentially affect it. But when I care about knowing that someone has stage B heart failure, really we're taking a three-dimensional object and have a two-dimensional image of it. The left ventricle, the thing that we're talking about is thick, really only kind of sticks out right here, and it's in between these two blue lines. So is my model learning what I think it's learning? And if so, why is it that I don't see something that's just focused on where left ventricular hypertrophy ought to be most visible, when this is an entirely different structure? Well, one of the problems is that class activation mapping techniques essentially show you what's going on in the final layer. And by the time you've reached the final layer, with convolutional neural networks, you've often continually decreased the total pixel count as you increase the total volume and depth of the image. So you may start out with an image that's 224 by 224, but by the time the model is done, it may be 64 by 64, 32 by 32. So inherently, what has to happen is at each one of these layers where you see average pooling, which will be these transition layers, you'll instantaneously see there's a degradation in half of the total pixel count. So of course, by the time you get out to here, you're only going to see something that's really, really broad. Instead, when we look at it, we can see the model is focused on much finer details earlier on. Another challenge, though, is this is DenseNet, and DenseNet architecture has what we call skip connections. So different convolutional layers apply to one another in various amounts. So the dense block here is a combination of all the dense layers that comes before it, but their total contribution to the dense block is variable. So it's hard to say that there's a clear and clean story from dense layer 1 to 6 or dense layer 1 to 12 in the next one, because their total contribution to this final layer before it undergoes max pooling or average pooling again is variable. So even here, when we start to look at it in a finer detail, it's hard for me to look at this and definitively say, aha, well, it really does seem to be focusing on the left ventricle here, and thus it is learning what I think it's learning. So there are very significant challenges that persist. So my concluding thoughts is that deep learning can profoundly improve medicine. My recommendation and what I've learned the hard way is pick problems that need solving, not just ones that fit your method. The best are the ones that do both. Make sure it's not a workflow problem. If it's the sort of problem where logistic regression is 90% as good and isn't being used in clinical practice, beware. It may be that there are challenges that have nothing to do with technical complexity that are preventing good solutions from being applied. We need better tools. We need faster, simpler, and more reliable experimentation and validation. We need people sharing code and making great libraries. And we need better ways to understand these models whenever possible. Not everything needs to be fully explainable. There's lots of black boxes in clinical medicine, but it helps when we can say, this is why we think this is the case. And lastly, you, and I do mean you, can have a huge impact. What I've learned over the last couple of years is that small teams can work at a huge scale when you have good oversight and great infrastructure. And finding places that provide you that, the way Odyssey does that for many people here, is immensely valuable. And many projects can have impact quickly. Not everything in medicine needs to move slow. And when you have good clinical collaborators, you can find those things where we're willing to test. And things change more than really any of us realize. Talking with my colleagues and seeing things that are now routine and feel like low risk, and understanding these were procedures that were extremely high risk and very scary just 10 or 15 years ago, makes me realize we have a long history of risk taking in medicine, and we have a general comfort with saying this is new, but we think this is better. Let's find out and let's test it. So a huge thank you to many people. I do want to shout out a few people. Tim Podoruca, who's my co-captain in all this work, a great friend and a great collaborator. Shreyas, Victor, who have been amazing lab mates and wonderful, wonderful people to work with. And Adler, who's unfortunately leaving us, but you know, I think we may have driven him to it. We were usually productive, but every once in a while we lost ourselves, and this is what happened during lab meeting when Adler explained to us there was a drawing and annotation function available within Zoom. So we will miss you, Adler, and thanks for everything.
Great. Thanks, Dr. Pierre Elias, for the great talk. I think that's an exciting project. See how the deep learning techniques can be, applied to help in the cardiovascular disease diagnosis, and also like you raised the great the problem that we have now about deep learning. Maybe it still remains as a black box, and it still lacks the interpretations of how the prediction or classification works, and how it can really help when should we really use it in the daily practice, right? So yeah, with that being said, yeah, I'm happy to open the floor for questions. Yeah, is there any questions? You can just unmute yourself and yeah, ask the questions.
Pierre, I had a few both comments and questions. So thanks for that talk, and I think that this area has a lot of promise. Some comments as someone who's done some phenotyping of amyloidosis, both AL and ATTR. We had a presentation in Odyssey symposium a couple of years ago, which found that you can get some differentiation of molecular subtype, at least in our data, based on the sequence of organs involved. And we found that AL amyloidosis tends to be diagnosed first in the kidney more often. whereas ATTR amyloidosis tends to first pop up in the heart. The other thing is just as the radiologist Simi wants to talk to you also about your deep learning model. And at a couple, so from what I saw, if I'm understanding this properly, you are using one view of the chest. And when I was looking at those x-rays, I saw a couple of things that surprised me. One, which was that in the heart failure x-rays that you showed, nobody had a pleural effusion. And the other thing was that I didn't see any lateral views, which could be a possible limitation for generalizability, because sometimes the first border to get dilated in heart failure is actually the PA border. And the third thing I noticed was that the patients had comparable inspiratory effort. And in thinking about patients with heart failure who may have concomitant COPD, kyphosis, other musculoskeletal problems, I wonder if these features, which were not present in the data set that I saw, could limit generalizability.
All phenomenal thoughts, and really interesting to hear about that with amyloidosis, because it does make sense, right? AL and ATTR, they share certain things, but there's lots of, I think, unique and hidden features that can come from looking at things at a large scale that we may not have thought about, right? Which is, where do you find it first? With the chest x-rays, it's a great point. This is a model that sometimes works beautifully and is sometimes frustrating. We did look at a lot of different chest x-rays, and Victor has some kind of amazing pictures of like patients who have, Victor, I still think of that one that you sent me a while ago. The heart's on basically the wrong side of the chest. There's like horrible kyphosis, and it's still keying in on the heart. So I think the true positives that are very high positive predictive value, it's going to be the easy slam dunk ones. The question of laterals, Shreyas did some amazing work where we looked at a huge number of things. So these images are 1800 by 1800, and then they get scrunched down to 224 by 224 to fit into like, the standard DenseNet 121 model. It's a huge amount of data that you're losing. So we tried bigger images. We tried APs and laterals. We tried including tabular data like their age and sex. We tried all these things and had no impact. For 9 months, I'd be like, I've got the next thing you should try, Shreyas. I know this is going to make the model better. No change. So it's really kind of been surprising and humbling. All of these things that we think would be clinically important have had very little impact on the model. And so, yeah, I think there's ongoing challenges of what's the right way to use these and what's the right way to apply. And I'm humble enough to say, like, we improve a point, which is that at least in some cases, there's a meaningful piece of information beyond cardiomegaly, something that's being left on the table. But maybe that doesn't apply for every case. And we still have to figure out when it does apply and when it doesn't apply.
There's another question in the chat. I think Jen asked about the importance of the false negative. As you mentioned, in the importance of positive predictive value for your model to be accepted. What about the false negative? Do you think a doctor might be less likely to order additional tests for a patient if that patient was incorrectly not labeled as high risk by your model?
Also a great question. So it's really important, right? And those are the sorts of things that we want those are the things we want the least of, right? We're okay doing some additional diagnostic testing, but the patient who has a disease that we miss and they go untreated, those are the things that leave us, that keep us up at night, make us feel terrible. But the thing to remember is that the way we want to run these models is basically run them on a population of people who have one imaging modality but don't have another imaging modality. So we're almost starting with everyone is presumed negative because you've chosen not to get this advanced modality on them. Whether it's you're trying to find valvular heart disease, they don't have an echocardiogram, you've made a choice that you've clinically seen the patient and you don't think they need an echocardiogram. So what's interesting here compared to a pure diagnostic test, right, where it's you're going to do it on everyone. Here, we're starting with a patient population where there's a bunch of people who are undetected. And so we're okay with missing half the patient population to begin with, because we're in deep learning version 1.0. And we're starting with a population where everyone's been missed already. Everyone who has the disease in that population has already been missed. So what we want to do, though, is we want to say, does any of this stuff even work? That's what keeps me up at night. I build this stuff and spent the last 2 years on it. I still have no idea. Is this really going to work? And so the first thing we have to do is just say, like, in the highest risk patients amongst all of this, does it work? And once we've proven that, then we can start to dial in. I do think there will be some cases where really high negative predictive value will be the thing that's valuable, right? Like there can be cost of care things where it's like, I just want to feel comfortable that I don't need to get this expensive test on the patient. But this is grantsmanship and all those sorts of things that go with an academic career. People are a lot more excited about finding new disease than confirming someone doesn't have a disease. And so that's kind of how we chose, like, these are things we think are important and why we want to focus on them. So sooner or later, it is going to matter, but we're still, we're in the alpha phase, not even the beta phase. And we've got to make sure this stuff actually really, really works. And this is kind of the easiest chance it has at working.
Thank you.
Yeah, I saw another question from Udina, right? You want to ask it yourself? Yeah, I saw you right.
Yeah, well, I know we're over, so sorry. But I was just wondering if so I guess it's for the project with the electrocardiogram predicting the echocardiogram, I was wondering how these conditions are diagnosed if the electrocardiograms aren't informative, and what, I guess, brought you to use the electrocardiograms to predict then these conditions.
Great question. The ECGs get done for a wide variety of reasons. And so they're just a very common, very common first step in clinical medicine, whether you're in cardiology or not. So it's a cheap test, and we do it looking for tons of things. And we also do it just to rule out a bunch of things. It's kind of, there's like a certain set of tests that, like, if someone's even kind of sick, we do, or things like that. So ECGs are useful for looking for lots of other diseases, but can we expand what they're useful in finding? Because really what they're just telling us about is electrical activity of the heart. And then we've overlaid on top of that information and meaning, right? It's a baseline physiologic signal. And then we've said, when you see this sort of baseline physiologic signal, it means X, Y, and Z. But there are certain diseases we have not been able to expand it to with, like, our insights to date. But maybe deep learning can help us expand the number of diseases where this baseline physiologic signal gives us meaningful information.
I have another question, actually. Thank you, Pierre, for this excellent talk. This is very interesting, and I finally got to see your work. Okay, so actually, I was a little bit confused. So you're saying that if there's a challenge of, let's say, a patient have multiple images, right? So you will train them, then you can get different results. So I was just wondering, eventually you, I guess, randomly choose an image to train on, and how to make sure that your model will be generalized to other patients, if sometimes it will not work for the same patient.
Yeah, I mean, it's a really hard problem. And hi, Hanqing, it's good to see you. So it's a really hard problem. So we, I'll start with this. So when you're training a model, some patients are going to have like 100 electrocardiograms, and some patients are going to have 5. Is it going to bias your model and worsen your performance if you let the model learn from every single ECG, knowing, like, you've got 100 ECGs on this patient, and probably means they were in the ICU and really sick, and so on and so forth. So should you allow the model to train on all of that data? So what did we do? We took one model where we said that patients can have a maximum of 5 ECGs per patient, and another model where it's like learn from all the ECGs. And when you train those side by side and you test them on the same validation set, the model that learns from all the ECGs does better. So that's just one use case, and maybe that's not always true, but it seems like more data still allows for a more generalizable model that even, really sick patients, or that kind of atypical distribution of results, can just be another form of regularization. Now, the question, though, is when you're testing the model prospectively and the like, how do you test it on a patient, right? How do you say, I know what is the case of this patient? So what we did is we just looked at the most recent ECG of the patient, but that was a cop-out because that just made it easy for us and we didn't have to deal with the fact that sometimes the model will give you very different information from the patient. Frankly, we never even looked to see how would it do and what is the inpatient agreement. Because, with some of these diseases, maybe the patient didn't have the disease before and does have the disease now. So maybe there should be disagreement, but it was a whole other layer of complexity that we just weren't even prepared for. And it takes so long to do some of this stuff where we said, well, we're just going to look at the most recent ECG and say, what's the performance on their most recent ECG? But I do think that we need to have some way of learning from patient priors and showing that there is some internal coherence between the patients. And know that that's how it's going to be able to generalize between patients or between sites. Multi-site validation has been incredibly difficult for all of these projects, despite an immense amount of effort to try and pre-process the data, months of talking through it all and things like that. We found it very, very tough when we go to totally different sites like UCSF or Stanford to get the data to match up. So there's real challenges. I think the models can be good to do exactly what it is you do at the site you do it, but probably need some degree of retraining at whatever other site you're planning on using it on again.
Yeah, that's a very good thought. I will also can resonate. That's a very, very hard problem. And you had anyway hard problem to start with anyway. So I was just wondering that at the beginning you said that if the feature is already very well identified, then actually it doesn't matter which model you use usually, right? Because the model perhaps would have the very similar results, which have to resonate from my past experience where we deal with registration regression versus other more complex models and the results is very, very close. And so I was just a wild thought when you're saying how to take into account the patient priors, is it possible actually to generate features to quantify these kind of prior versus history, as if you do, let's say, ECG or time series of heart rate data, where you generate those features to used in your model. And I understand that one of the merits of deep learning is to get around this feature engineering which is very painful usually. But that might be just one thought, I guess.
It's a great thought, yeah. And we need more research. Is there a single latent space, if you're using encoders, that does a better job of this than the way convnets work? Or we tried Fourier transforms and all these sorts of things, but we need something that can learn from priors in a better way. And we need easier ways to know two models are actually focusing on similar things, right? What if you train two models and it turns out they're focusing on entirely different things, even though the data, just when you make a slight difference in the pre-processing or the like. So there's, I think, many ongoing challenges of saying, yep, this model is learning what I expected to learn, and that fits within what I think it needs to focus on to be translatable to other sites.
Okay. Thanks everyone for the great talk. Yeah, and also I see people are excited about the discussion of the deep learning because it's really bring us, it's very useful to help us in various different ways. So given the time limit, we have to cut it off here. And if you have further questions, please send the email to Dr. Pierre Elias, right? Yeah, again, great talk, and thanks to everyone for being here. Yeah, I'll see you guys next week. Yeah, bye, take care.